Okay, so we start the last session of the workshop. Our first speaker is Daniela Cocchi from University of Bologna. She will be talking about spatial entropy. So speakers have 25 minutes. We leave a few minutes for discussion. Thank you.
Well, my thanks for the invitations. Are particularly warm because the invitation itself induced me to think to statistical problems in a different way. Because if I had to illustrate what we are doing, I think that I'm working in related problems. But I tried, and with my co-author, tried to understand. And we succeeded in thinking that we can work with our idea also on the change point problem. And indeed, I have to thank very much my co-author, Linda Altieri, that is at present on maternity leave. And so she works when she can. On Sunday, some hours, moments like this, and so we communicate a lot with Skype, and this is a very, very, very good way of working. Moreover, I have to say that we are a national Italian group that we call with an acronym EFASTAT that try to connect environmental problems with health problems. And a little bit we succeeded in this, and we have a very good personal relationship, and we are at the end of this 3-year project. The point is how can we deal, the starting point for us was how to consider space in statistics. As many speakers in these days told, the point is that at the moment we have a data set about a study variable that may be only univariate, there are other dimensions, at least the 2 geographical coordinates to take into account. And so, roughly speaking, space may be considered in sampling, and when we speak about spatial sampling, there is also immediately the expression environmental sampling that comes into the fore, or in estimating some population characteristics in non-parametric or parametric way, implicitly assuming simple random sampling. So there are these 2 facets of the problem. Given that we started from the point of spatial sampling, I have to say that in service sampling, space can be considered in 2 ways, or modifying the inclusion probability, or for the when we use the typical estimating tools of finite population, where we do have the inclusion probabilities that are something that alterate the condition of IID. And what does occur when space is considered? That there is a kind of data spatial correlation. In other words, a lack of independence that is due to space that can be considered or in negative or in positive ways according to the fact that we try to exploit it or we avoid it without being aware of the problem. So this is the setting. But there is a very important, there is a very important topic in statistics that come from information theory. It comes from the second law of thermodynamics, indeed, and it's the notion of entropy. In statistics, the notion of entropy is something that can be seen as an important version of variability. And is a lot of work essentially done by René has been made in order to consider at the same time entropy in the continuous or in a discrete case. However, the entropy is the expectation of the information function, and it allows to compute a measure of variability in statistics without having the value of the variable, without keeping the values of the variable into account. So it has been very, very popular in the non-statistical realm, in the realm of linguistics, in the realm of biology, in the realm of a lot of situations where the fact of having a quantitative variable, or at least an ordinal variable, is very important. And so a lot of statisticians worked a lot on this topic with a lot of semi-applied papers that, in synthesis, tend to repeat the same thing. This is really something that was very astonishing for us, but we understood, consulting a lot of literature, that indeed many papers that pretended to be very original repeated the same thing without deepening the foundation themselves. And moreover, classical entropy measures are not affected by spatial structure. Because for a given variable, let's say x, if there are different spatial structures, the same entropy variable value is delivered, unless one tries to modify entropy. And there are many studies have been made in order to try to keep the population spatial structure into account. And some modifications have been introduced, starting, the best ones are those of Batty at the half of the 70s, that were inspired by some works of Tile. And indeed, what Harry Tile wrote on spatial version of entropy can really be considered as interesting. Then there was a very strange paper of Carlstrom and Ceccato that has very, very, very good ideas written in a very strange way, because they try to exploit the idea of local and global entropy. Then there are more recent works of Eichler and Hu, or Naim and others, that are much more recent. And we also have a proposal that has been summarized in a series of papers. When we speak, but this is entropy for the variables, because there is another way of speaking about entropy. When we are in the world of sampling plans, there is a search of sampling plans that have enjoyed the property of maximum entropy. This is completely another thing, because the entropy that is considered in sampling entropy is the entropy of the sampling plan. So the element, it is a completely discrete measure, and the objects that enter in these definitions are the probabilities of the sample. And the main writer on this topic has been Jaroslav Hayek in 1981, and his work has been followed by the one of Yves Tillet, that wrote a fundamental book in 2006. But this writing is completely different, because the value J is the number of samples in the population. It's not a property of the variable. And so the confusion, for us at least, was strong, because we had to understand what we were trying to work about. Indeed, when we speak of entropy in sampling, there is a very strong role of the inclusion probabilities. The inclusion probabilities, surely each of you is an expert of finite population inference, but in finite population inference, there is the winning estimator is a so-called Horwitz-Thompson estimator, which gives to each member of the population, that may give to each element of the population a different probability of being included in the sample. The simplest way of having this inclusion probability is to have them all equal, so we reduce ourselves to the problem of simple random sampling. But a lot of information that is external and that is not included in auxiliary variables can be introduced in inclusion probabilities. And these inclusion probabilities are seen as basic weights that are to be assigned to any element of the population. In finite population inference, we are always 10 years late because of the problem of the size of the sample and of the size of the population. This seemingly easy inconvenient really induces a lot of difficulties. And the point is that when an Horwitz type estimator is proposed, it selects one part of the population inclusion probabilities, but the inclusion probabilities have properties that are enjoyed in the population and not in the sample. And so there are many difficulties linked to this point. But if data are spatially correlated, I ask you to keep in mind that a good sampling plan ought to produce similar estimates whatever the spatial structure is, because the spatial structure is a kind of accident that has to be neutralized at the moment that we estimate a characteristic of the population. Many researchers worked and tried to modify inclusion probabilities in order to obtain a good balancing, because the idea is that a sample has to be good, has to be considered well spread, and on this there is a lot of discussion, because at the final point, the best estimator following this idea ought to be a purposive sample and not a random sample. So a lot of discussion, a lot of papers linked to this, and the confusion is linked to the fact that many special statistical tools rely on the idea that units that are near in space tend to have similar values. This is a typical law of geography that is always motivated every time that we speak about spatial statistics. So there is a strange confusion between the spread of labels, I call it sampling entropy, and the values of the variable, and I call it spatial entropy. But there are names. Everyone can use the names that he wants, and maybe there are better names in the literature. It's not my problem. But the challenge that we can have is how using some components of the spatial entropy measures as weights. How can we introduce the idea of spatial entropy? The idea is forget the classical expression of entropy, because it is univariate. It is very, very peculiar. Rather, try to exploit the bivariate properties of entropy. But in order to do this, we cannot consider the initial variable z. There is to transform it, and this transformation has occurred in many, many papers on pseudo-spatial entropy, without saying this clearly, a transformation that we call, with another name, z of x, that witnesses the agreement or disagreement between the realization of x can be proposed. And this variable has to correspond to the unordered pairs of realization of x over the observation area, because ordered pairs have no sense in spatial analysis. And but all the researchers that worked on Z considered one distance at a time. They worked conditional on a given distance. So our micro idea was to introduce a second variable that classifies all the Euclidean distances within the observation window according to a set of distance classes that can be fixed in advance. Only in this way it is possible to write this. This is a very known relationship of entropy theory, but say that the marginal entropy of the variable z and not of the variable x can be decomposed in the sum of a a thing that for spatial convenience we call spatial mutual information, that is a weighted average of elements that have the form of a Kullback-Leiber distance. And we call this spatial partial information. The same additivity properties is also possessed by the HZ with the W at the foot that is called the residual entropy, but indeed is an average of conditional things. And indeed, now we want to attract your attention on what we call SPIs, but also the HZ has partial components too. So after this idea that we try to sell in some places, and we had to think about the way of using it in some way. Where was it possible to use this proposal? The idea was to introduce it in what is called the spatially correlated Poisson sampling. The spatially correlated Poisson sampling is an iterative sequential procedure that tries to modify, and succeed, to modify the initial inclusion probabilities in order to keep into account of something that is linked to space. In its formulation, it modifies the inclusion probabilities with that multiplier that is called B. B is a factor that weights in how the sampling of a unit is affected by the previous one. They work running along the population that is indexed by two letters, K and L. This strategy that has a certain fortune in finite population inference is called maximal weight strategy. The point is that we tried to do a very stupid thing, but only in order to understand to what extent it's possible to propose, to use our idea, to substitute the BKL with our distance, with our spatial partial information, the conditional distribution of that. And so we say that for all the elements that fall in the same distance class, we use a certain weight B. Instead of constructing that B only with respect to distances, we consider the spatial partial information. We tried a simulation study with 4 spatial configurations, a very compact one, a binary variable x that has 400 realizations, so the proportion is always 1/2. But the 1/2 can be arranged in the 4 ways, the compact, the chessboard, the multi-cluster, that is very interesting, and the random maintaining the same proportion. And we tried only 4 classes. We made many rehearsals, but they say explaining what we mean, we proposed 4 classes. The number of classes might arrive at the size of the population. These are the partial terms in the 4 spatial configuration. We make a simulation with 100 samples of size 40 from each data set. This is an example, one simulated sample for each configuration, but please note that the sample is not the same because it is extracted independently. When we compare this to maximal weights, and for the maximal weight there is an air package balanced sampling, and there is to note that when the 1,000 samples are produced with the maximal weight system, they are the same whatever the spatial configuration. On the contrary, in our proposal, we keep into account the 4 configurations. So what do we obtain with only 4 classes? That, as expected, the maximal weights and the competition is assessed in terms of the mean square error of the Horwitz-Thompson estimator. The compact configuration is better reproduced with the maximal weight system, but the multi-cluster is better explored with the spatial partial information weights, because this idea can be explored in this way. In this case, we are estimating the mean. If we estimate the total, we have to multiply everything for the square of big N. So where are we? We look for the communication between seemingly separated words, because spatial entropy and sampling entropy seems really to are similar but expressed with different languages. And so we want to deepen the means of considering the important contribution contained in spatial partial information, and we want to explore ways for estimating the probability entering spatial entropy. The probabilities that enter in entropy have good properties if they are estimated with the maximum likelihood. So they are good if they are substituted by the empirical frequencies. But these empirical frequencies do not keep space into account. So our idea is to do this. But I want only to sketch that spatial entropy measures can be of help also in the detection of change points in urban development. We had this idea when we were invited to this conference, because before we forgot to have produced papers on space-time change point analysis, because we completely modified our point of view. What is urban development? There is a definition of a metropolitan area. There is to understand that after the Second World War, the industrialization and the fast urban development pushed the states in order to achieve adequate urban plans. And there is an unpleasant consequence that is called urban sprawl. Urban sprawl has a lot of sociological definition, but more or less, for us, there is to understand that it stressed the uncontrolled city expansion over rural or semi-rural areas. If a city is too sprawled, you have also to use the car. This is the point, because the school is there, the market is there, and there is a lot of lost space. So the measure of urban expansion should be interesting in this way. Urban development can be measured with entropy, because landscape metrics are a very popular, relatively popular, 20 people in the world, because we are speaking about this amount of amateurs, can be considered as a popular tool. There are integrated indices that are very difficult to achieve. For simplicity, ratios of urban growth can be used, or also the population densities that have some faults. But what is important? It is important that at the European level, there is a system that is called CORIN that contains all the classification by pixel or raster. There is a deterministic modification between pixel and rasters in order to detect an urbanization pattern. So it's possible to measure urban development with entropy with some advantages and with some against, with some bets. And we already worked on this. We had some papers, and we proved that the spatial entropy measures succeed in evaluating the level of urban expansion. So it is possible to detect change points in the evolution of urban expansion. We think yes, because we made some previous work applied to the first one applied to the radioactivity in a beach in the north of Scotland, and another one with an application of earthquakes in Italy, and we worked in order to try to face complex spatial-temporal data sets, where the assumption of independence between observation within the same time segments is unrealistic. And the spatial entropy measures are a very good data summary for this, because it is possible to produce a binary segmentation algorithm that is an iterative procedure which looks for each single change point for the whole data set. If we found it iteratively splits the data at the change point, dealing with the resulting segments separately, until no more changes are detected. The advantage is that this is very simple, and the number and the position and change points are estimated sequentially at the same time. Which are the approaches to change point detection? There is the change points in the traditional entropy, where a temporal series of Shannon entropy is used, but space cannot be kept into account. A3, we call it model-based change point detection that we used, but we are insisting on change points in spatial entropy. Why? Because this, that I call A2, is easier and faster to implement than with respect to A3. A1 is good, but does not have any ability to detect changes in the spatial configuration. So, indeed, we checked that spatial entropy performs well not only in studying the urban configuration, but also in finding changes in the spatial behavior of urban development over time. Here we have some bibliography, some references, and apart from our avoidable ideas, people that it interests have to read the work of Batty, the work of Tillet, the work of Hayek, in order to keep, to grasp what is the importance of the proposal. Thank you.
Questions? Let's thank our speakers. And the next one is Georgi Terdik, that talks about cumulants and skewness measures in the multivariate setting.
Okay. Thank you. First of all, I would like to thank for the invitation and the nice organized workshop here. And if you see, my courses are the Srinivas Jamanamadaka and Emanuele Taufer. So the skewness and kurtosis is a very well-known and studied subject. Okay. No, I'd like, yeah, okay. And okay, maybe. And if I shall talk about a bit moments and cumulants, and then the method, the actual technique we are using for studying these multivariate problems. And then the multivariate skewness and kurtosis, and then testing. So not too many new results I'm showing, but there are some interesting points when we studied this problem and found it. So in the classroom, it's easy to understand what the skewness and kurtosis. The skewness is basically the symmetricity, and the kurtosis, if you look at the Gaussian density, which is a kind of ideal shape, and then you compare to that one both the symmetricity and the shape of the curve. So this is the skewness and kurtosis if you want to explain it. But analytically, if you look at, then the skewness is going to be the third-order central moment, or the third-order central moment is the same as the third-order cumulant, and the kurtosis is going to be the fourth-order cumulant, which is not anymore the fourth-order central moments. It's a bit different if you look at the expression according to in terms of the higher order moment. So this is something like different than that. So understanding the cumulants, that's a very important point in this study. And also, if you look at the multivariate case, so when you look at the multivariate case, the expected value is pretty much known, saying that you take it by the entries. So the result is a vector. Now the second order central moment or second order cumulant is a matrix. So in that matrix, as a covariance matrix, you will have all possible pairs and the cumulants of these all possible pairs, or the variances and the covariances on that matrix. So the question is, what's going to happen if you go further? What is the best way to look at the, let's say, the third order central moment? So the third order, you have to take all possible product of orders 3, and then you might put them into the matrix, then it's 3D matrix, and if you go further, then you will have a 4D matrix, and so forth. So it's really hard to follow this point. I only found one suggestion in the Kolo and Srivastava. So they realized that if you take the second order, so this second order is going to be a matrix, but it is the same as you take the tensor product of these two. So what they are doing, you start with one, and then you put the second one is a transpose, and now they are continuous. The first one is just the vector itself, and then they transpose, then you put a vector again. And the shape they suggest to follow is take a vector, transpose, and so forth. But unfortunately, analytically, you cannot handle this. And what is the best way to do so is vectorize. So it may be vectorizing the covariance matrix. It might not sound good, but vectorizing the higher order moments, it will work. And I remember yesterday, Jan Beran mentioned that vectorizing is a natural way to look at the higher order moments. Okay, so therefore, we shall vectorize it. So, and vectorize the moment and vectorize the cumulant. And vectorizing it is a good technique, because if you look at the moments in terms of characteristic functions, so this is going to be a series expansion according to the tensor product of order k, expected value, and then you take the tensor product of the variables here, and the same thing is going to happen with the cumulant. Take the cumulant generating function, and the same pattern comes out that you will have this variable up to the tensor product k, and then the coefficient here is going to be cumulant. So, so keep together the same order, cumulant and moments. This would be the way. So looking at only the vectors here. Now, the name. So the name, usually people saying the Kronecker, sometimes direct product, and sometimes the tensor product. So we shall follow the tensor product, and basically because the derivative I suggest here is different than derivative Jan Beran mentioned yesterday, because my derivative is like take the Jacobian and transpose it and then vectorize it. And the result is that we shall have a function and take the tensor product according to the derivative vector. So this is going to be a natural way to, let's say, to get the cumulants and the high-order cumulants, high-order moments, and multivariate case from the characteristic function or from the cumulant generating function. We had this derivative, and I applied it for the nonlinear, non-Gaussian multivariate time series problems. So that's what I did in 2002, and also with Jamala Marakarao and Suvarao, we used this also for nonlinear multivariate statistical problems, and it turns out that this technique works pretty nicely for this problem of multivariate skewness and kurtosis. And just one property of this derivative, so it will be called T derivative because of the tensor product here. So the T derivative, when you are applying the second times, it naturally comes by the end, the second derivative, and so forth. Of course, it's not just, you cannot do it just directly, because, of course, it's not commutative. But the tensor product, luckily, is commutative in the sense that there are linear transformations to commute two tensor product, the tensor product of two vectors. And this linear transformation, you give a matrix. So I'm using such type of matrices. I shall show one of them or two of them. And in this way, if we take the derivative of the cumulant generating function, then we shall have the cumulant. So no matter of the dimension of the x, so I have here from 1 to n possible with different dimension vectors, and this d is the dimension, and then for that vectors I can calculate the nth order cumulant as a vector. Well, usually it's a huge one because if you go further, then you got d up to the n elements of the vector, and this is going to be the nth order cumulant of that, not necessarily the same dimension vectors. Okay, so looking at the different dimensions and the different vectors, it helps a lot even when you are taking all the vectors are the same, and then you got the usual n-order cumulant of the one vector, but it helps in the sense that the pattern comes, you should follow. It show up nicely when you are taking different axes. Okay, so there is a well-known formula that you can express the moments in terms of cumulants, and of course you can express the cumulants in terms of moment and so forth. So there are several nice formula on that. But I follow this Lukács method, which is in general the Fadi-Bruno's formula, saying something about when you are take the derivative, the compound functions, what pattern comes out. And this is the same thing when you are taking the derivative of the log of the characteristic function. This is a compound function, and when you are taking the derivative, you should follow what kind of pattern comes. And here is a multivariate version of that. So you are interested in the nth moment of the vectors x from 1 to n. I mean, this is all of them might be different dimensions. The dimensions are here, but the order is going to be the nth order. This is a 1n means just 1, 1, 1 vector containing all ones. Okay, so here you have the cumulants. Now the cumulants, you should take the tensor product of them. And here are the matrices I was talking about. These are, we call it commutator matrices. Commutator matrices is doing a kind of permutation of the tensor product. So if you have, let's say, a permutation here, and you have a tensor product of order n, then this matrix will change you in the order what is written in this permutation here. And then the summation is supposed to take over all the partitions of the numbers from 1 to n. So for a scalar case, it's quite clear, this formula, but for the multivariate case, you have to be careful with these matrices, commutator matrices. Well, actually, we shall not use it more than order 3 and 4 because of the third order cumulants and fourth order cumulants, which are the skewness and the kurtosis. But this is a quite general, nice formula for it. Okay, so from now on, the skewness we shall mean a vector. This vector, okay, so this one is going to be centralized, and we look at the centralized third order moment, which actually the third order cumulant in that case. And this is a vector. So this vector contains all the possible third order product of y, so including the cubes, including the square and 1, and all different distinct products. So, and actually, if you look at this tensor product, what's happening? It's happening that the third order power will show up only once for each entry of the vector. But let's say if you take all the distinct ones, then it will show up 6 times. So there are a kind of symmetricity in that vector. So, and this is what we have to take care on. Okay, and now the measure of modia is just the modulus of modulus of that skewness vector. So we just say that this is a skewness vector. And all the other measures, we shall express it in terms of this skewness vector. And it turns out that there are a couple of called different measures, but only there are some which are different. Okay, let me show what I mean on that. So this is the Mori-Rotagi Seikei, and they are defining it as take the matrix here, like a covariance matrix, and then take the product by y, and we can express it in our skewness vector like a tensor product. This is a unit matrix here, d-dimensional, and then you will get the Mori-Rotagi Seikei measure. So actually it is a vector. So the Madia's measure is a scalar. Now this is going to be a vector of dimension d. And some people criticize that this vector will not contain the third-order cumulants from that gamma when all the indices are different. So therefore, the suggestion of Kolo is that take another type of measure, but it turns out you have to be careful because we found the vector gamma, which is can be a third-order cumulant, and then this measure is going to be 0, and this third-order cumulant is not 0. So this measure does not fulfill a basic requirement that it shouldn't be 0 if the cumulant is not 0. And the next one is the Malkovich-Afifi. They suggested that if you have this cumulant vector, look at the direction where it is maximal. And then if you have this direction, then you take the projection on this direction, and that will be the possible measure of the skewness. But it turns out this is nothing else, just the Madia measure. It is quite natural that the direction where it is maximal, it is the same direction as our cumulant vector now. So this is not another measure then. And the next one is multivariate version of it. So if you want to get not a scalar measuring the skewness, but you want to get a vector measuring the skewness, then it turns out that this is Balakrishnan suggested that it turns out that it's a constant times the Mori-Rotagi Seikei measure. So this is not another measure again. So there are not too many measures around, even people claiming them. Okay, so we can suggest one because this is going to be just a linear transformation picking up all the distinct element of the skewness vector. Let's say this is a matrix G, and then we shall have the distinct elements of the skewness vector. This is a G up to the capital D, and this is the dimension is here is not D up to the 3, but a bit smaller than that, and we can also use it as a scalar measuring the skewness. So this is one chance to take the skewness measure. So we looked at several distribution and used this technique, and we got much easily than some paper calculating the higher order moments and the higher order cumulants for this skew distributions. And let's say I just show it the Skew-normal one. Then when we look at the Skew-normal one, so there are parameters here which are the 5 minutes? Okay. So this is the next. Now, lemma is just saying that the cumulants of higher order cumulants is pretty simple for the skew-normal. Okay, you have to figure out the constant here, but otherwise it just goes as a tensor product of the delta and so forth. So these are the two constants here, what is interesting for us. Okay, so these are the distribution we looked at. And now the point is if you want to test, so you have to estimate the skewness. Okay, so estimating the skewness is first of all, okay, so we have a sample. We have a sample here, and then we centralized. And centralizing is by the estimated variance and by estimated mean. That's very usual. And now we look at the skew, calculating the skew vector for the y, but from the y, naturally we can get the original skewness of the sample. But what is the point here? That if you look at the mean of this is third order centralized moment of the vector. And okay, so this is going to be to estimate the cumulant, but then it turns out that it's nothing else than the third order Hermite polynomial, multivariate, and take the mean of that. So, and what we mean on the third order Hermite polynomial is just the same as we usually. Each entry is a third order Hermite polynomial. Okay, depending on the entries, I mean some of them are same and some of them are distinct and so forth. So now what we are really interested in, what is the asymptotic distribution of the third order Hermite polynomial. If I put inside the y is not Gaussian, but H3 is the third order Hermite polynomial for a Gaussian one. Okay, so we have the expression. I just want to say here that if you look at this expression, so this is a polynomial in terms of the tensor product, of course, but this is a polynomial of the cumulants. So this polynomial of cumulants is called a pair polynomial. That's it. And then we look at the Gram-Charlier expansion. And now the Gram-Charlier expansion is showing clearly what the meaning of cumulant. So the cumulant showing how close you are the multivariate Gaussian distribution. And if you look at the coefficient here, the first two coefficient is 0. That's fine. But then from 3 to 5, the coefficient according to the Hermite polynomial here is the cumulant. And then if you go further, we need for the kurtosis, we need the 8th order cumulants. So therefore, the 8th order situation and the 6 and 8, we have this formula for the cumulant. We are looking at the cumulants of the HK when you are putting into the it's our sample then. And the important point here that this one is a Gaussian density. So everything is going to happen according to the Gaussian density, and the Hermite polynomial is according to the Gaussian density. Okay, so it's quite easy to see what is the general pattern. So we are looking for the expected value of the tensor square of the third order Hermite polynomial, this one, and of course, as usual, we can put it in terms of the Hermite polynomials up to the 6th order. Okay, and this one show up some other Hermite polynomials and also some other cumulants, but when I take the cumulant, because the mean is 0, so the second order cumulant of that one is just the mean, then we shall have, well, here is commutator matrices, This is a symmetrizing matrices. But we have a nice formula in terms of the cumulant. In terms of the cumulant, this is a 6th order, 3rd order, 4th order, 2, and so forth. And when we put the hypothesis that the skewness is 0, it means that this term will disappear. So we shall have a nice expression for that. And we have, okay, the point here that this is a vector. So from that vector, you have to go back to the covariance matrix. But it is reshaping. So reshaping a vector, you will get a matrix. It's not a big point. But when you actually want to show something on that matrix, I'm the covariance matrix, it is a bit work to do so. So this is going to be the pretty general testing hypothesis that skewness is 0. And, well, we have to look at the problem because we haven't put the true value for the mean and the variance. So this is what you have to take care of and so forth. But the result is very, very simple for Gaussian case. For Gaussian case we have this covariance. So this covariance is just saying that, well known, of course, that it is going to be Gaussian and high square d plus 2 over 3 degrees of freedom. And well, the elliptically symmetric distribution, that's a bit more work to get the hypothesis testing. This is, first of all, we need the higher order cumulants of the elliptically symmetric distribution, which turns out pretty simple because this one is the marginal cumulant. So what you need a marginal cumulant to get the higher order, but otherwise it's just quite a simple expression on that. And okay, and then, well, we shall get the same what Clark got in 2002. So now I turn to the kurtosis now. Thank you. The kurtosis is very parallel.
Georgi, and we move to the closing with Lorenzo Trapani.
Thank you. How do I get to my presentation? Where is the thing, the clicker? Yeah, it's here. But thank you. Okay, well, then, thank you very much to everybody for your incredible stamina in staying here until the very last presentation, which, as you might have deduced, is me. And I have the privilege, I say it without sarcasm, to be the last one to say thank you to the organizer for such a wonderful event, which I was not aware of, and now I look forward to the next one, should I be invited, of course. This is joint work with Emily Whitehouse, who used to be a PhD student at the University of Nottingham, where I work at the School of Economics, by the way. As you will probably see from the presentation, she's now moved to Newcastle. The paper, the title, I think tells quite a bit about what we're going to do. It's going to be a contribution in the field of checking if there is a change point, but the change point will be in the future, hence the expression sequential monitoring. And we will be dealing with a special case of a linear model where the regressors are non-stationary. We call it co-integrating regression. I know that you know better than me, but just to set the tone of the talk. But perhaps I do not know whether you will find the paper per se interesting. I do not know whether you are incredibly interested in co-integration. It is fair to say that people employ it, but it might not be the thing that we are incredibly interested in. I do not even know whether you think that sequential monitoring is the most interesting thing, or if you prefer testing for breaks. Maybe during this presentation I will also try to show you something from the point of view of engineering on which we try to construct a monitor in statistics, and it is something that could be exported also to other contexts. It's not limited to the context of co-integration. So I think I've been talking enough. So we will be referring to equation 1. Okay. This is the model which I have in mind. As I promised, it's going to be a co-integrating relationship. So if you keep looking at the equation, yi and xi are non-stationary. As we like to say in econometrics, they are I1 variables. You take the first difference, they become stationary. You know better than me. Epsilon I is stationary in some sense, hence the expression co-integrating relationship. We have a time sample, now look at me please, that goes from 1 to capital T, and 1 was in the past, capital T will be in the future. Today is M for mother. We've seen the data from 1 to M. We are satisfied with equation 1, whatever this means. Beta has not changed in the past, it was correctly specified, whatever. We would like to see from tomorrow M plus 1 onwards, and I leave this quite ambiguous, up to T, which could go to infinity, maybe not, we'll see it later, but we would like to see if this model is stable, if it stays as it is or if it changes. And I guess, if you look at equation 2, that there are so many ways in which an equation could change. I'm going to say something that is incredibly obvious, but you see why I say it later on. It is natural that under the null there is no change, and the null hypothesis seems to suggest that there are two changes that could worry me. One is a change in the slope beta. I would like it to be constant, and I think that we can buy into this idea. And the second change that could happen, for reasons that I would like to clarify later, is that I want the error term epsilon to stay stationary. So equation 1 was a co-integrating relationship. It has to keep being a co-integrating relationship. What would happen if it were not? When we talk about the alternative, I'll tell you. But for now, that's, so to speak, the null which I have in mind. It's not exactly the first contribution I appreciated that you see in the context of monitoring a linear regression. I think that in the stationary case, forget about co-integration, in econometrics there is a paper by Chu, Stichcomb, and White, which for some reason is very, very famous. It's the typical paper where the authors employ some sort of weak invariance principle, and they do the things that people do with weak invariance principles. If you want something that gives you better power, so to speak, you can move to slightly stronger forms of convergence, and there are two contributions by Horvath, Kokoska, Steinebach, and the 2004 one also as Marie Hushkova. Especially the 2007, I think, is one of the best written papers I've ever read. It's so clear. And in those two papers, the authors extend the weak convergence world to a strong convergence world, and they derive results which we can claim are better. And this has to do with monitoring for changes in linear regression models. If you are interested in co-integration, there are contributions. Ansgar has one. I think probably one of the first ones that was written. Dominic Wied and Martin Wagner and their PhD student, who is this lady, Neslihan Sakaria, are working on a series of projects on checking whether an equation, like equation 1 on the previous slide, changes over time or not. So there is interest in this sort of literature. I don't want to tell you what we do, but I would like to finish the literature review by telling that we will, in our paper, only use rates. So there's not going to be convergence to anything. But, okay, there are rates, but there's not going to be a limiting distribution anywhere. Maybe because we are lazy, maybe because we didn't know how to derive it, but there isn't. We only use rates, and then, given that rates are rates, where is the randomness? We put the randomness. And we use a technique that we call randomization, which it is fair to say has been around for quite a while. In econometrics, there are several papers in several areas. I've got one with Lajos on a completely unrelated topic. We will see how that works. And I would like to try and tell you what I was saying at the very beginning, that you may not be incredibly interested in co-integration per se. Not everybody uses it. But when we were working on this contribution, what I liked was how inexpensive it was to derive results. Because I've always had this idea, maybe I'm wrong, but I've always had this idea that working out a limiting distribution for me is very difficult. Studying a rate for me is comparatively easier. And so if I can exploit rates and don't have to work out a limiting distribution, my life becomes easier. You can feel free to call it the lazy man approach if you want. However, I think that it is fair to say that there are cases in which maybe the asymptotics is not necessarily trivial, like the Darling-Erdos results that, for example, you find in the Horvath, Kokoschka, and Steineberg 2007 paper are not a trivial extension of results that already exist. And sometimes you may find it prohibitive to work out that asymptotics. Or there could be cases in which with pencil and paper you know how to work out the limiting distribution, but then there is a parameter which you know how to estimate, but you do not trust the estimator in practice. Some people say that long-run variances are notoriously unreliable. I don't know if that's true or not, but if you believe it, you may have a problem if you need to estimate one. You may have the error term epsilon I, which has heavy tails, and we know how to estimate a tail index, but we may be worried that our estimator is not amazing. We could have long-range dependence. We may need to estimate that h exponent. We know how to do it, but again, we are a bit worried. Or we may be in a context in which the tail index I was mentioning earlier on changes over time, and we don't want to bother about that. All we want to know is if beta changes or not. That's all. So in all these cases where the limiting distribution could have nuisance parameters or difficulties that you feel uncomfortable about, it is possible that this approach might be, like I said, a possible alternative avenue. Let us remind ourselves what the main equation is. It's that one. I really want to keep my promise. The regressors xi are non-stationary variables because they look like, I don't know what you call it, an integrated process. As far as the notation is concerned, there are a couple of long-run variances that I would like us to consider. Maybe this one, which is the long-run variance of the epsilon i's, could be of interest or not, but it's only notation. Usually, when you do a presentation, they ask you to lay out the assumptions. And I'm happy to do it just to show that I presume that the assumption that you see there, which helps us study what happens under the null, is not the most exotic assumption ever. All I'm asking is some sort of approximation of these xi, which are partial sums, to something, and I don't know whether this delta should be particularly good or not. As long as it's greater than 0, it's fine. And I find it very interesting that my colleagues who work with weak convergence, sometimes they assume weak dependence. So they say the data are strong mixing, blah, blah. Sometimes they don't. Sometimes they say the partial sums follow a weak invariance principle. And this is my assumption on weak dependence. And we do the same. Except all our rates are almost sure, and so we want something that is a bit stronger. But that's all, in essence. The rest of the assumptions, I insist, are things that with IID could be verified with pencil and paper and even not with IID. So probably the assumptions were rather canonical. The null hypothesis, in some sense, goes without saying. Nothing changes, or nothing that is of relevance to us. We consider two alternatives because we thought that they might be of interest to the applied user. I believe that if the beta in a linear model changes, we can all agree that that is important. So that's the first alternative. A non-mutually exclusive second alternative that was brought to our attention is that the error term epsilon I was stationary up to today. Today is m, I would like to remind you. But maybe there is a point in time, which we call k star, after which co-integration breaks down, and so epsilon I becomes non-stationary. And some people say that this is interesting because maybe yi, where is it? Yi is prices of something. Xi are fundamentals that drive them. If you've got this relationship as a co-integrating relationship, prices are driven by fundamentals. If you don't have co-integration anymore, some economists have pointed out that that could be evidence that there is a bubble. And this is a structural explanation of a bubble, not a time series explanation. And although I don't fully understand what a bubble is, I see merit in even considering the case that epsilon I could change could become non-stationary, and so you no longer have co-integration. So those are the two alternatives that we were interested in considering. One could consider even more meaningful alternatives, I'm sure. The previous assumption was to study the stuff under the null. When there is the alternative that epsilon I becomes non-stationary, I really mean that it becomes non-stationary, and I will assume something that is similar to what I assumed for the regressors xi earlier on. It's just the first thing that came to our mind. Monitoring is something that you can do as you want. There is plenty of flexibility. For example, look at me, sample from 1 to m, you estimate beta, and then you don't update the estimate any longer. Or you can update it. In the papers by Lajos, Piotr, and so on, there are both things. We would like to just consider this example here, where you estimate beta once and for all, and then you don't update it. But I guess that it's an extension that one could consider. Then, from m plus 1, so from tomorrow onwards, I get the residuals. In general, I like the idea of considering the residual sum of squares over time. And I know that I am dividing by the long-run variance of epsilon. I know it. And that's because the unit of measurement of epsilon, I need to get rid of it. But my claim is that since as I only care about rates, if this estimator is not incredibly amazing, my life is not going to change. I mean, if you go to infinity, you go to infinity. If you go to converge to 1 point, a billion numbers after the dot, we can decide that maybe the accuracy of an estimator should be interesting. So this is going to be my cumulative process that I'm going to use to detect if there is a break or not. The idea is that this guy will keep growing under the null that there is no break, but it won't grow too much. If there is a break, this guy freaks out and you realize it. You see a huge, huge change. So look at this guy here, and there are plenty of other statistics that one could consider, but look at that guy there. Incidentally, very briefly, I wanted to estimate the long-run variance. I insist that if the quality of this estimator is very poor, my life doesn't really change as long as I get rid of unit of measurement. So I propose the typical weighted sum of covariance estimator, the cheapest possible. With brute force, I find a strong rate of convergence. There are papers that do this job a much better job. I think again, Piotr with Istvan, Berkes, and Lajos have a paper on the strong consistency of the Bartlett estimator. As long as there is an almost sure rate there, I'm a happy man. So I've got an estimator for the long-run variance. It is consistent, proven by brute force. The rate is almost sure. I can move on. I can tell you that under the null, I was talking about rates, wasn't I? And for some reason, I enjoy almost sure rates, just for the elegance of the results. I can promise it to you that under the null that there is no change. This guy here, my statistic, Q, will grow, but this growth is bounded. And it is bounded by this expression here where, apart from the log terms, some of which come from sophisticated results, others from brute force approximation, apart from the logs, I don't think that this growth rate is overly surprising. So this is how it should grow in terms of an upper bound under the null. Under the alternative, I guess, I'm not even reporting the result because I can guess that by construction, look at it. For example, if epsilon I becomes non-stationary, this is the square of the Brownian motion. These are the partial sum of the squares of the Brownian motion, so it will grow like the sample size squared. So it will grow more. So there is a discrepancy in how you may diverge or converge between null and alternative. And I insist, it's only rates. Now, normally when you do monitoring, you know better than me, there has to be a sort of threshold function. Look, this is the threshold function. If Q stays in between over time, then there is no break because it's growing naturally. If Q crosses up or down, no, then there is a break. And this function is defined like this, and it is the classical function that one would use generally speaking, apart from this gamma greater than 0, which serves the purpose of separating massively what happens under the null, what happens under the alternative. My idea is that if I take Q and I divide it by G, under the null it goes to 0, almost surely. Under the alternative it goes to infinity, almost surely. My idea is that there is a major discrepancy in the rates. And I can tell you how fast, by the way, but that doesn't matter. So this gamma, there is a bit of tuning. It's something that in the paper we more or less discuss how to choose. It's probably more an empirical matter, but there is some discussion. We want our monitoring. Tm is capital T minus m. For how long do I monitor? We want to go on for quite a while. In fact, for a long time we wanted to go on. We thought that this was interesting, but personal opinion. So I told you that if we do the ratio between our statistics and the threshold, we get this guy here. And by construction, I expect that it goes to 0 under the null. And by construction, I expect that it goes to infinity under the alternative. And I have no idea what else it does because I am a bit stubborn and I don't want to work out a limiting distribution. Maybe because it's difficult, maybe because I'm lazy. I really like, however, this behavior that you go to something which is 0 or something else which is infinity. I love this separation result, so I want to play with it. So instead of considering psi, I will consider a variant. This variant has an exponential because, as I said, I really like that there is a discrepancy between 0 and infinity, and I want to emphasize it. But I would like to consider the opposite behavior for reasons that in a second you will see, convoluted reasons. Unelegant reasons, but I would like under the null to go to infinity. And under the alternative, I would like to go to 0. And so I invert, so to speak. So now the idea is that in theory, under the null, I should go to infinity, and under the alternative, I should go to 0. But don't forget that whatever I do, psi tilde, for every k, k is the day when I monitor. Every day I wake up at every k, I compute psi tilde with this laborious procedure. And psi tilde is 0 or infinity, roughly speaking, because it goes there. It's not that it is there. But there is no randomness. So what can I do? I introduce the randomness. It can be done with very clever algorithms. This is a convoluted algorithm which I myself don't particularly enjoy. It has become popular in the econometrics literature. I thought of using it, but as soon as you see how it works and what purpose it serves, you can come up with better algorithms almost on the spot. So this is the idea. You got psi tilde. Think about the null. Think about the null. Under the null, psi tilde is infinity. Come on, roughly speaking, it's infinity. So give me an artificial sample of dimension r. How much is r? We'll talk about it. It's a big number, but we'll talk about how to choose it. You choose it, so you choose it in a way that's comfortable for you. So you've got a sequence which is IID normal 0, 1, as big sample size is r. You multiply your sequence by this psi tilde. So under the null, this is the normal 0 infinity. I want to be a bit rough. And then you construct this Bernoulli variable, which is 0 or 1, like a good Bernoulli. And how often is it 0? How often is it 1? Well, what's the probability that the normal 0 infinity is not greater than some number, u, which you like and you've chosen? And if it is the normal 0 infinity, I guess that this is a Bernoulli variable, 0, 1, probability 1/2, probability 1/2. That would be my guess. So now I've got a sequence of IID Bernoullis, 0, 1, 1/2, 1/2. So the expected value is 1/2. So if you give me a sequence, and I take away the expected value, and it is 1/2, I haven't got it wrong. Now this is a zero mean sequence. You add it up, you divide by the square root of r, and what do you get? So this guy here, under the null, should converge to a normal 0, 1. And if you don't like the normal, you can square it, and you can get a chi-squared. And if you square it, you may be able to integrate out u, because your choice could be different from mine, and we could consider this a lack of scale invariance, if we like, roughly speaking. So under the null, you have created this guy here, for this theta capital letter here, which at every day k will converge to a chi-squared with 1 degree of freedom. Then there are theorems that prove it. And I appreciate that this is a very interesting intermediate result, because I'm not trying to say that if you converge in distribution, the moments also converge. There is work to be done. But at least we've got an idea of what that guy is going to. Under the alternative, psi tilde goes to 0. If psi tilde goes to 0, this is the normal 0, 0. If this is the normal 0, 0, this is still a Bernoulli variable 0, 1. What is the probability that the normal 0, 0 is smaller or equal than u, if u is a positive number? I think we know the answer. So 0, 1 with probability 0, 1, or the opposite, I've forgotten what I was saying. But certainly this Bernoulli under the alternative is 0, 1, not 1/2, not 1/2. That much I do know. If this Bernoulli is 0, 1, not 1/2, not 1/2, the expected value is not 1/2. So here I made a mistake when I subtracted 1/2. And I'm adding up these non-zero mean variables, and I am dividing by the square root of r because I made a mistake. And then I square to make the mistake even worse. So I guess that under the alternative, you have created a sequence at day k. You have created a sequence which is a very big guy, as big as r. That would be my guess. When you do this job at every day k, it is your choice what you do, but I would say that these CKs can be independent every day. So even the sequence, theta, whatever it's called, even this guy here is independent across k. And k is the days when I monitor. K is equal to 1, tomorrow. K is equal to 2 days' time, blah, blah, blah. So you've got a sequence whose behavior you may guess, although a bit more work is to be done. And this sequence, under some regularity conditions, and under some restrictions which give you a choice for r, there is a bit of tuning. Under the null, you converge to a chi-squared. Intermediate result, more work is required. Under the alternative, you diverge at a certain rate. Result on which we will build. And now you have killed your data. Your data were called epsilon hat, the residuals. You've canceled them. You don't want to know about them anymore. You have replaced them with this theta sequence, which is IID, and whose behavior, with a bit of work, is that of a chi-squared with 1 degree of freedom. So it looks like a sequence whose mean I should be able to prove is equal to 1, and whose variance I should be able to prove is equal to 2. And then what you do is you kill your data, you replace them with this newly generated sequence, you subtract its asymptotic mean, and a bit more work is required because I don't know if it converges to 1, but then I prove it. You divide by the asymptotic variance, square root of, and again, ditto as above, and you do what everybody would do in monitoring. You create this monitoring function here for every day k, and this cumulative process, under the null that there is no break, under the null this guy is a chi-squared, roughly speaking, so this has mean equal to 0, so this is an independent sequence which has been normalized. So I can manage with this new sequence. With this new sequence, now all I have to do is plagiarize the results that Piotr, Lajos, and other people have derived. Because now it's results for an IID sequence whose behavior I can control, more or less. And given that I can control its behavior, I define, how much time do I have? Okay. I will define this, I don't know if to call it threshold function. Here you can see what the literature is about, because there is this eta here, which customarily we set equal to 0, and then we are able to use weak convergence, and then we are a bit disappointed with the power of our procedure. And if we want eta to be a bit bigger, it cannot be 1,000,000, it stops at 1/2, but if we want eta to be greater than 0, then weak convergence is no longer usable. Fine. But I get more power, so I'm interested. But my point is that we are using this 26 equation here with an IID sequence, which is totally under my control, so I don't have to create any new theory. I can use, like I said, the theory that someone else has developed for me. And if I can use the theory that someone else has developed for me, why don't I use the theory that someone else has developed for me? So I do it. And I've got this weighted norm convergence result, which is the same as in the 2004 paper by, well, the same, give or take, by Horvath, Kokoska, Hushkova, and Steinebach. Or I've got this Darling-Erdos type result, which is the same as in the same author's 2007 paper. I can tell you that the procedure is consistent, if that is the right expression for monitoring. And there is some asymptotic size control, although when we do the simulations, we are very happy that the false alarm probability, the monitoring, don't forget, goes on forever, for a very, very long time. So we are very happy that this false alarm probability is very, very small. It's not the nominal alpha, because that would be a bit of a disaster if you go on forever sooner or later. And we are, like I said, once again, consistent if this is a different way of writing this consistency which I am referring to. And that's the end of the presentation, because I can promise to you that if you look at equation 1 in the previous slides, there is no constant, there is no linear trend, but we could introduce those deterministics. We do it in the paper. The price to pay is minimal. We can try to study local alternatives, considering that we've got infinity and zero as divergence. Speaking of local alternatives is an abuse of terminology. But we can try to understand, at least heuristically, what happens if the beta changes, or if by how much it changes and how this affects the power. So we can do that sort of study, and we do it in the paper. I can tell you, because I'm sure that I look very reliable, that the Monte Carlo went quite well, because ultimately these techniques are not techniques that are surprising. So in some sense, whatever Monte Carlo we did was very similar to the Monte Carlo previous studies. Of course, we did the same thing, so how could it be that different? But it works quite well, I've got to say, and we were quite surprised to apply our test to US house prices. Apparently, there is a famous study in applied econometrics where this guy studies a cointegration relationship, and he finds out that it's no longer a cointegration relationship after 2015. And he says that's because there was a bubble on the US housing market. I take the author's judgment. It's a very nice paper. So we pretend that today is, I don't remember, 2009, and we see and we try to monitor. And we apply our technique, and we manage to find the break in cointegration at some point in time. A previous study where they use eta equal to 0, so weak convergence only, presumably because strong convergence with integrated regressors, stochastic integrals, is not easy to digest. I don't know why. But they don't do it. They find failure of cointegration, but they find it 11 quarters later. If you look at the graph, the failure of cointegration is here. After 1 quarter, we see it. If you look at the other study, it takes them 11 quarters, which is a longer time. So I know that this is not a simulation, that these are real data, that everything is subject to discussion, but we were interested in this result. We thought it showed some potential. And I think that that's it. So, thank you.
Are there any questions?
Can I ask one question? So your results, they are valid on the assumption. So if I understood it correctly, you assume that the xi's are like random walks,
Yes.
Integrated. So is there potential for this method to work if you have something like, say, fractionally differenced model for the xi?
I am working, okay. In my opinion, there is potential, but a good answer should come after working out the maths. I'll tell you what I'm working on. I'm sorry if I make it long, but it's interesting that you should mention it, because you and Lajos have a paper on a smooth function m of t plus an error, and the error I think is weak dependent or IID. And I wanted to consider this a smooth change in trend. Temperature data could be an idea, but I wanted the error to have long-range dependence. And I have it's a topic in which I'm not ignorant. I'm the most ignorant person in the world, so what I say could be wrong. But I had a feeling that the dependence on H was there. And I wanted, and maybe H could also change, the Hurst exponent. And with this technique that is based only on rates, there is such a gap between the null and the alternative that A, I don't need to know H, B, if H were to change, I wouldn't care, within reasonable. If H becomes a trillion, maybe I would, but will it become a trillion? So there is potential, but it's an ambiguous answer because I haven't worked out the maths yet. But thank you for the question. I think Holger had a...
One quick remark. If I remember correctly, you regarding your monitoring scheme, you just took the sum from n+1 to n+k.
Yes.
There's a better one, I think, which we have recently developed, and there's a paper coming out in JASA where we really improve these monitoring schemes.
Which I will read.
No, I will send you.
Oh, please, thank you.
Yeah, no,
I will read it with great
You
interest.
can do better, and then we also have results that you can use in the last step. I think.
Thank you very much.
Yeah.
Thank you.
So let's thank you, Lorenzo. He had to wait quite a long time to deliver the talk. He was actually the first to come to the conference. It was so... And it was so early that since I didn't know him, I thought he was a student, so I didn't talk to him. So we close here. Let me thank you, all the speakers, for the variety, the quality, and the interestingness of the presentations, and I hope that we will have the occasion to do another workshop in some other location. Okay, thank you very much to everyone.